we'll continue where we left. So we were talking about the derivative and how we can have some functions that have the first, the second, the third derivative, however many you want, but then the fourth derivative does not exist or is not continuous, right? The fourth derivative exists, but happens to not be continuous because of this reason of oscillating too much. And let me remind you what we did last time. So we looked at examples like this. So this one is the function x sine of 1 over x. And for this one, we know that the derivative does not exist. This function is continuous, so continuity is fine. But right here, where it is at 0, the derivative does not exist. But if we make it x squared sine of 1 over x, that now these oscillations are bound between two parabolas. Now the derivative does exist at 0. The derivative right here exists and is equal to 0. But the second derivative itself is not continuous. All right, so not, sorry, I said it wrong. The first derivative exists, but it's not continuous. Okay, that's what I meant to say. So the first derivative exists right here. It equals 0, but it is not continuous. Now, if we go one more, and some of this is part of your explorations on example problem number 7 on this section. You're going to need to verify all of these properties that I'm telling you about. This one, if we go x cubed, now the derivative does exist here, the same. The derivative is 0 right here at the point 0. But this time the derivative is continuous. So everything makes sense. All right. Now you may ask yourself, hey, what about the second derivative? Can we take the second derivative of this one? And the answer is yes, you can take the second derivative, except at 0. At 0, the second derivative will not exist. Now you want the second derivative to exist at 0, then go to the fourth one, and so on. So that's part of what I'm telling you, this exploration that you need to verify on example 7. All right, so let's go back to the page and talk about this Darboux's theorem. And so what we just said is that there are functions. E.g., this one's over here. If x is not 0, and 0 if x is 0. There are functions such that their mth derivative exists, but not their m plus 1th derivative. Or the m plus 1th derivative exists, but it is not continuous. Okay, but the important point is that discontinuity is of the essential type, meaning it's discontinuous because it oscillates too much, right? Thus, the discontinuity is essential. And we ask, that's how we started this chapter, this discussion, if we could have a derivative with a jump discontinuity. So that was our question. So can we have a function f such that f prime exists, but it has a jump discontinuity? Okay, and the answer to this question is no, and that's what we're going to be doing today. So actually, the first derivative happens to have the intermediate value property, right? So the answer to this is no. And what we just said is that the derivative in general, f prime has the intermediate value property. Remember what this property means? So it means satisfying the conclusion of the intermediate value theorem, meaning if you achieve one value and another one that are, while one bigger than the other, then you achieve anything in between, right? So I'll write it here. E.g., if you have two values such that they sandwich some other number, or the other way around, then there is some constant, some number between A and B, such that f prime of C equals L, right? So that's the intermediate value property. So if you achieve two values between A and B, you have two values, then you must achieve any other value in between. Okay, so even though this function may or may not be continuous, yes, so the derivative may not be continuous. And even though the derivative may not be continuous, it still satisfies this property, right? So it satisfies this intermediate value property. All right, so we're gonna see this, and before we do this, in fact, this is actually not a difficult theorem. This Darboux theorem is actually quite straightforward when you think a little bit about it. And the reason it's not that difficult, this is because it's based mostly on these other little results that you should know quite well because you used it all the time in calculus. Is precisely what motivated the definition of critical points or critical values. So this is theorem 5.2.6 in our book, and it's called the interior extremum theorem. And it says the following. It says, if you have a differentiable function on an open interval, and it attains a maximum value at some C in AB. What does this mean? It means that this value f of C beats everyone, right? It's greater than or equal to f of x for every x in the interval AB. So that's this f of C is the biggest of all, the largest of all the values. If that happens, the derivative at C equals 0. And the same is true for minimum values. So this is the classical theorem you guys used in your first semester of calculus to find out maximums or minimums, right? We used it the other way around. How? Well, you started with a function and you check that it has a derivative. Most of them have derivatives. And then you checked where the derivative is 0, and those were your candidates for maximums or minimums, right? We call these points with 0 derivative, we call them critical points. And so it was based on this theorem, right? So check the points where the derivative is 0. Those can be maximums or minimums. Or also where the derivative is undefined, right? Because then this theorem doesn't apply, and that those may also be maximums or minimums. That was the way to use this theorem, all right? And okay, so let's prove it. It's actually not a very difficult theorem to prove. This is also relatively simple. How do we do it? In fact, I sort of provide a little explanation in my own calculus class when I teach this. So what is it? How is it that we do it? Well, here's how. I'm going to use sequences because that's what we mostly developed in this course. So you can certainly, so let's do a little picture here. So here's our interval AB. And somewhere there is C, right? And what I'm going to do is I'm going to construct a sequence of points, two sequences, one approaching C with values smaller than C. So from the left is what we would call it, right? Like one sequence that goes like this and it's getting close to C, x1, x2, x3, etc. And another one of Y's that approaches from the right. So two sequences, one of values less than C and one of values greater than C. So let xn and yn be sequences such that xn is always less than C, yn is always bigger than C, and they live in this interval. Now, and it can be any sequence. If you want more specific, I mean, you can, of course, create these sequences, right? You can maybe do C minus 1 over n. You could use that one if you want. And C plus 1 over n. You can use that one on this side. Assuming n is big enough, all of those will be in here or in here, right? So let me write here. If you want more specificity, you can use C minus 1 over n and C plus 1 over n for n large enough, right? Maybe at the beginning it doesn't work because maybe A and B are too close to C, but eventually those this could work. All right, and then what's the idea? Well, we have to use the fact that we have a maximum at f of C, right? So let's enlarge our picture to considering our function. So let me throw it over here. So here's my new picture. So here's A, and here's B, and there's C. And we have some function, and remember, well, let's do the case where, let's first do the case where the maximum is C. So we're gonna have some function, and that function achieves its maximum at f of C. Maybe something like this, right? And then we have our sequences, the x's and the y's. Okay, and now what I want to know is what happens with these points, right? When I take them up, how do they look over here in the function? Specifically, I know that f of C is the largest of them all, right? So this height is f of C. And that f of C will beat any of these guys, right? F of xi or f of yi. It's bigger than all of them, all right? And that's exactly pretty much the only property that I need. Okay, so let's start with the x's. So I'm gonna write here, note that f of xi minus f of c is strictly less, well, it's less than or equal 0, right? Because this guy is the maximum. I mean, maybe some of them are as big. That can happen. It didn't happen in my picture, but it is possible for some of these heights to be as equally large as f of c. So equality is possible, right? And this is because f of c is the maximum value. I should have said that we were doing that case first. So over here, assume f of c is the maximum of f on AB. Okay, so that happens. So this is less than or equal to 0. So now we want to relate it to the derivative at c, right? So what is the derivative of c? Well, the derivative at c by definition is the limit when x approaches c of f of x minus f of c over x minus c, correct? And in particular, I can do this limit with any sequence that approaches c. So I can pick sequences. I didn't write, I said it, but I didn't write it, that these sequences, so the limit of the xn is c, and the limit of the yn is c. So these sequences are approaching the x sequence and the y sequence, both of them approach c. So this is the limit when n goes to infinity of f of xn minus f of c over xn minus c. And let me change this to n so that the indices match. All right? Okay. So now what? Well, now take a look at the sign of this number, right? What do we know about the sign of that number? Well, the numerator is less than or equal to 0, right? And how about the denominator? Well, x is to the left of c, right? So the denominator is also less than or equal to 0. So therefore, when you divide a negative number by a negative number, is greater than or equal 0. I'm gonna write it here. Because f of xn minus f of c is less than 0, and xn minus c is less than 0. So that happens, correct? So I know that the derivative has to be greater than or equal to 0. And then all I need to do is repeat this argument, but now with the y's. So similarly, f of yn minus f of c is also less than or equal to 0. And thus, if I look at the derivative, this time I'm going to use y. So the limit when n goes to infinity of f of yn minus f of c over yn minus c. So what is the story now? Well, this time the numerator is negative, same as before, but this time the denominator is positive, right? Because yn is to the right. So now you're dividing a negative by a positive. So this is now less than or equal to 0. Because, right here, because f of yn minus f of c is less than or equal to 0, and yn minus c is greater than or equal to 0. So this time they have different signs. Therefore, this is less than or equal to 0, right? And then that's it, right? Putting these two together, if the number is simultaneously greater than or equal to 0 and less than or equal to 0, there's only one logical possibility left, which is that f of prime of c is equal to 0. Hence, f prime of c equals 0. All right, and we only did the maximum, but the minimum can be done the same way. If you do the minimum, the difference is that now this guy will be positive, and this guy will be positive. So over here will be positive divided by negative, so it will be less than or equal to 0. And over here will be positive divided by positive, greater than or equal to 0. So if you're going to get the same thing, you're going to get that it is equal to 0. So if f of c is a minimum, then The same argument works. Okay. All right. So this is it. Whenever we have a maximum or a minimum, the derivative is 0, right? Assuming the function is differentiable in that interval, assuming the derivative does exist. Okay, great. So that's mostly our preparation needed for the next one. So now let's write down Darboux's theorem, the one we were talking about. So this is now theorem 5.2.7, Darboux's theorem. And this is what it says. It says if f is differentiable on the closed interval AB, all right? Notice, this means it's differentiable at the endpoints. So this implicitly assumes the function is defined in an interval even a little bit bigger than AB. Because remember, to define the derivative, we need to have a neighborhood around a point, right? So if this happens, and f prime of A is less than alpha, less than of f prime of B, or f prime of A is bigger than alpha, bigger than f prime of B, then there is a point C in the interval, open interval AB, such that f prime of C equals alpha. So in other words, the derivative satisfies the intermediate value property. The derivative f prime satisfies the intermediate value property. Okay, is that clear? So this is now what we want to prove. All right, let's do it. How do we do it? Well, first we could do it just directly with alpha, but then first there's this little trick that simplifies things so that we can think that alpha is 0 all the time. Okay, that we're wondering what's happening around 0. All right, so that's our first simplification, and it's just as this is actually not necessary, but it just clarifies things. It makes things easier. So here's the first thing. So let g of x. So we're gonna construct an auxiliary function, and this will be f of x minus alpha x. Right. So let me also only do one of them. So let me do the one where is it the first one that I want to do? I think so. So assume f prime of A less than alpha less than f prime of B. So we'll do the first case. The other one is symmetric, similar. Okay, so we created this auxiliary function. Why? Because notice this g is differentiable as well, because f is differentiable, so we can do the derivative here. And this is just a line. A line is also differentiable. And the difference of two differentiable functions is differentiable. So this new function is differentiable. So note that g is differentiable on AB, closed interval. And what is the derivative of g? Well, it's the derivative of f minus the derivative of alpha x, which is just alpha, right? So now, if what I wanted as my conclusion is that there's a C such that f prime of C is alpha. If that C satisfies that f prime of C is alpha, then over here I'm going to have alpha minus alpha. So now instead of looking for something equal alpha, I want something equal 0. And that's the part that I was telling you. So we want to show, let me write it here, there is C in the interval AB such that G prime of C is 0, right? It's somewhat easier to think for something equal to 0 than for something equal to alpha. All right, and now here is the way we're going to do it. We're gonna take a look at the derivative at A, right? So let's look at G prime at the point A. So consider the derivative of G at A. Okay, time to start a new paper here. So what is that? Well, that is G prime of A. What is it? Is the limit when x approaches A of G of x minus G of A over x minus A, right? So that's the derivative at A. Now, remember, right now A is our left endpoint. So let's do a little picture here. So here's our situation. We have A and we have B. And
Professor?
yes.
Can you move the paper just a little bit to the side so that we can see the end?
Sure.
Thank you.
Let me probably. Okay, so this is our picture. We have the interval AB, and we're considering x's that are getting close to A here. Now remember, that means the function is actually defined a little bit wider than just in the interval AB. So the domain must have a little bit to the left as well. But never mind that for a moment. And let's look at the points that are to the right of A. So imagine that x is to the right of A. Now, suppose for a moment that so what do we know about G prime of A? Well, let's go back. So this is the definition, but also G prime of A is actually f prime of A minus alpha, right? It's just the definition here. And what do we know about f prime of alpha by assumption? As I have it right here. F prime of alpha is less than alpha. So this number is less than 0, right? So the derivative right here is less than 0. Yes? And because it's less than 0, and if we imagine that x is to the right of A, so if x is to the right of A, so if we consider, so here's what cannot happen, right? So x minus A is actually positive, right? So suppose that, imagine for a moment that the top gx minus g of A is positive for all x such that x is bigger than A. Imagine for a moment that happens. Can that happen? Could this be a possibility? Well, this means x minus A is greater than or equal to 0, right? So look what we have right now. We have that this is positive, and so is this one, x minus A. Well, that would be wrong, right? Because then over here, the numerator will be positive and the denominator will be positive. And positive divided by positive would give me a positive number, right? So then the limit will be positive. So,
Professor?
yes.
In regards to, well, initially when you said that the function kind of exists outside of A to the left,
Yes.
can you kind of explain why that's so again? Because I'm just trying to tie it in with the G of X idea here.
Yeah, I'm not using that right now. I just wanted to let, so yeah, the fact that so what was our definition for the derivative, right? yesterday when we defined the derivative.
Uh-huh.
The derivative at a point requires you to have a little interval around that point.
Right.
Because it's defined by a limit, right? So if the function here was not defined on the left, then then you cannot talk about the limit, right? For the limit, you need a neighborhood.
I see.
Mm-hmm.
Right. Makes sense.
So in this case, the point that I'm trying to make is that right now I'm only considering x's to the right of a.
Makes
That's
sense.
really all that I care for this theorem, right? We want to show that there is some c in between. So I wouldn't use x's on the left because that would be worthless for my result. Mm-hmm.
Gotcha.
Okay. So going back to what we were saying, see, it's impossible for these to be positive for the values that are greater than a, because then both of these would be positive numbers, and then the derivative would be positive. So this is impossible because then gx minus g of a over x minus a would be positive, would be greater than or equal to 0 for all x's greater than or equal to a. And so g prime of a, which is the limit, would also be positive. Which is false, right? Because we said that the derivative is actually negative, right? So this supposition then is wrong. This supposition is not right. This one over here, yeah? So what does that mean? Well, it means that this doesn't happen for all x's, right? So there must be at least one x, so there must be some x where this is the other way around. Mm-hmm. So let me write that down. Therefore, there is a point x naught such that x naught is bigger than a, and g of x on naught minus g of a is less than 0. So we must have a point that is actually less than 0. Mm-hmm. All right? Okay. Now we're gonna repeat the same with the point B. Okay, so all of these that we did with A, we're now gonna do with B. So I'm actually gonna write it down this time so you can see that there's nothing hidden here. So again, so it will sound a little repetitive. So recall that g prime of B, what it was g prime of B, is f prime of B minus alpha, and now this time this guy is positive, right? So therefore, this limit of g of x minus g of b over x minus b when x approaches b is positive, right? Now, the same thing. Suppose that g of x minus g of b. So now now this is positive. So the contradiction would be that this would be negative, right? X minus b is negative, so it will still be greater than or equal to 0 here for all x, such that x is less than b this time, right? Because now I'm gonna use x's to the left of b. In fact, let me write, to avoid confusion, let me write y here. We'll make it look better. All right, so we know this is positive. The top one is positive. So assume the top one is positive, but then for every y that is less than b, so then the bottom is negative, right? And positive divided by negative, that would give me negative, right? So again, this is impossible. This is impossible because then g of y minus g of b over y minus b would be negative, which is false. Well, would be negative, and then the limit would be negative. And so g prime of b, which is the limit, will be negative, and that's impossible, which is false. So I'm just repeating the argument, and so that means this supposition again is wrong. Let me mark it. This one is wrong, and if that one is wrong, then that means this doesn't happen all the time. So there must be a point where the opposite happens. So therefore, there is a point y0 such that y0 is less than b, and g of y0 minus g of b is less than 0. So this, by the way, makes it so that y0 cannot be equal to b. I didn't say that before for the other case, but if y0 is b, then this would be 0, right? So we can actually put strict inequality here. So this can be strict, and so can be this one over here. Right? They can both be strict, because if x0 equals a, then this would be 0, and it cannot be 0. So therefore this happens. All right? Okay, so let's analyze then what we have achieved. All right, let's stop and contemplate what we have done so far. So what is it that we've accomplished? We found 2 points, a point x0 and a point y0. And what we know is that x0 is bigger than a and satisfies that g of x0 minus g of a is less than 0. And we found g0 less than b with this other property. Okay, so let me write that together. So far, we have x0 and y0 points in the interval AB, such that g of x0 is less than g of a, and g of y0 is less than g of b. Right? Okay. So you may be wondering, where are we going with this, Professor? Okay, so you got these 2 points with these properties, and what's the point? Well, here's the point. The point is this, that our function g must achieve a minimum and a maximum, right? Because we have a closed interval. Remember that? By the extreme value theorem, we know that continuous functions send compact functions, compact spaces, compact sets into compact sets. Therefore, if you have a closed interval, it must achieve a maximum, right? That was the extreme value theorem. So we must have a maximum and a minimum, right? So let me write that down. By the extreme value theorem, since g is continuous, right? G is differentiable, and we also saw that all differentiable functions are continuous, right? We know that g has a minimum value on AB, right? And then, okay, so it does have a minimum value. Now, where is this minimum value? Could that minimum value be at A? Could g of A be a minimum? can the minimum happen at A? That's my question here. What do you think?
Yes, because it's included, maybe?
Well, in principle, for an arbitrary function, yes, the minimum could happen inside the interval, or it could happen at the endpoints, right? That's in general what it happens. But look, four lines above, what is it that we showed? See, we showed that g of A beats g of x0, right? G of A is bigger than g of x0. So what does that tell us?
That is not the minimum.
That is not the minimum, right? Because this is an even smaller value, right? So g of x0 is even smaller than g of A. So then g of A cannot be the minimum. So can the minimum happen at A? The answer is no. No, because g of x0 is less than g of A, right? Can it happen at B?
Nope.
No, same reason, right? And that's why we were doing all this work. No, because g of y0 is less than b. That's the entire reason we were doing this. So if the minimum doesn't happen at A and it doesn't happen at B, it doesn't happen at the endpoints, then the minimum must happen in between, right? That's the only conclusion. So therefore, like my paper, sec. Therefore, the minimum happens at a point C in the open interval AB, right? It doesn't happen at the endpoint, so it must happen somewhere in between, right? Okay, and if it is the minimum, what did our previous result said? It's a minimum and it happens for a differentiable function. Therefore, by the previous theorem, what is the derivative of at C? It is 0, right? The previous theorem, what we learned is that if you have a maximum or a minimum, the derivative right there is 0, right, of a differentiable function. If you have a maximum or a minimum in a differentiable function, the derivative is 0. So that's it. We succeeded, right? We find a point between that has 0 derivative for g, right? So if you have a derivative less than 0 in A and greater than 0 in B, then there is a point in between that has 0 derivative. And we did it for 0, but that shows it in general because then what is f prime of C? Well, g prime of C, by definition, the way we define our function was f prime of C minus alpha. So this is 0. And that means f prime of C equals alpha, right? So as a consequence, we show that the derivative of f happens to be the intermediate value we wanted, the alpha value we wanted in the first place. Okay, and that's the end. Now, we only did it in the case where so let's go back all the way to the beginning of the proof. So at the very, very beginning of the proof, we considered this case where f prime of A is less than alpha, less than f prime of B. If you want the opposite, then instead of looking at the minimum, you're gonna look at the maximum. All right, so the argument will work the same way, but instead of looking at the minimum, we're gonna be looking at the maximum. All right, just to let you know. All right, okay. Still have the end. So we have it right here. All right, questions? Okay, then we'll move to the next section, which is called the mean value theorem. If that rings a bell, that it should, because it's again one of those important ones that we used in calculus. In fact, the mean value theorem is essentially the tool required to prove the fundamental theorem of calculus, right? Which is, you know, the pinnacle of the results in calculus. So let's go back. Let's show the book. All right, so here's the important picture that explains the mean value theorem. This one over here, right? So this is what the mean value theorem says. If I always like this picture because it reminds me of the statement. That way I don't need to memorize the statement. So what this mean value theorem tells me is the following. If you have a continuous function, like the one you see on the screen right now, is continuous and is differentiable between A and B. So it's smooth, right? Differentiable means the tangent line exists, right? And so if you take a look at the straight line segment that joins the endpoints, so from here to here, right? You take a look at that straight line segment, you can always find a parallel one, a parallel segment like that, a parallel line to that segment, which happens to be the tangent line at some point. So in other words, if I move this one around, I should be able to place it so that it becomes the tangent line of some point in between. And obviously that happens right here, right? You see how I moved the segment and I now made it so that it is tangent. And that point where it is tangent, that point C, will satisfy what is written right here, which is that the derivative at C, because the derivative is the slope of the tangent line, the derivative, which is the slope, has to be the slope of that segment, right? And how do we get the slope of a segment? Well, it's the rise divided by the run. And the rise would be from here to here, right? That would be f of b minus f of a. And the run would be from here to here. So that would be b minus a, right? B minus a is the run, right? From here to here, and the height would be the rise. So the rise divided by the run is f of b minus f of a over b minus a. That's the slope of this dotted line, and that dotted line has the same slope as the red one that I moved, and that red one has a slope f prime of c because the slope of the tangent line is the derivative, right? So that is our mean value theorem, and we want to prove it. Okay, so let's show the statement, and then we'll proceed to prove it. So let me clear these little drawings, and then we'll move to the statement. So here is the statement of the mean value theorem. And if we have a continuous function that is differentiable on the open interval AB, so it's continuous in the closed interval and differentiable in the open interval, then it has a point in between that makes this happen, right? F prime of C equals f of B minus f of A over f minus A. All right. And the way we usually prove this is by proving a variant of this for the case where that slope is actually horizontal. And that is the so-called Rolle's theorem. So let me go back to the page, and we'll start with that one, and then I'll show you why that one is equivalent, essentially equivalent to what we want to prove in all generality. So here it is. We'll start with Rolle's theorem. This is theorem 5.3.1. and it's called Rolle's theorem. And it seems to be a particular case, but it's actually pretty much the entire thing. So this is what it says. Let f from AB to the reals be continuous on the closed interval AB and differentiable on AB. If f of A equals f of B, then there is C in the open interval AB such that f prime of C is 0. All right? That's what it says. And this is the picture that goes with this, this version of Rolle's theorem. So here's the situation. We have a function that is continuous in the interval AB, and this part, f of A equals f of B. So both of them have start at the same height. And then doesn't matter how I draw this, if I draw it smooth and continuous, right? Like maybe like that. So that's y equals f of x. Doesn't matter how I do it. There must be some point which has zero derivative. And in the example that I just did, I have 2, right? So this one works because the slope is horizontal. So 0 derivative means horizontal, right? And the same happens for this one over here. But okay, we only needed 1. So it really doesn't matter, okay? So this is Rolle's theorem, and as you can tell, it's kind of like the mean value theorem, except the mean value theorem was crooked like this, right? So the line was not necessarily horizontal. In this case, it is horizontal, and that also suggests how you can get one from the other. Okay, so let's prove this one. Proof. Okay, so it's actually easy. All we need to know is the theorem we need to use again. See, here's the thing. The proofs for these theorems all seem really, really easy and straightforward. And that's a little bit deceptive because they are based on other theorems we proved before. Specifically here, we proved the extreme value theorem. And that was a tough one to do, right? To show that a function attains its maximum and its minimum. For that one, we had to know about continuity, and we had to know about compact sets, right? The proof we presented here, in fact, used open cover, right? We extracted a finite subcover, all of that. So it was complicated. So there's a lot of work involved here, and now it seems easy because we're sort of collecting the fruits of all our work, right? I mean, we planted all those little saplings of little theorems, and now they grew into beautiful results, and we're using them to move further along. So here's the thing. So because the function is continuous here on a closed interval, then by the extreme value theorem, f has a minimum and a maximum on AB, right? Okay. So now where can this minimum and or maximum happen, right? Well, if either of these two happen at the endpoints, right? Remember that f of A equals f of B. So let me write it here. Recall that f of A equals f of B. So the endpoints have the same height, right? Both endpoints have the same height. Now, if the minimum or the maximum, if one of them, what is it I want to say? If both of them happen at the endpoints, if both the mean and the max happen at the endpoints, well, then the function is constant, right? Isn't that clear? So you have the same height for A and B. This height over here. And imagine that this is both the minimum and the maximum. If it's the minimum and the maximum, that means the function is just a line, right? It's a constant line. And if the function is constant, then indeed any point in between, right? If it's a straight horizontal line, then any point in C works. Any point in between will work. In this case, f prime of C equals 0 for any point in the interval AB. Pick any point, and that point will work. So that's if both the minimum and the maximum happen. So then what's the other case? The other case is that one of the extremum values, either the minimum or the maximum, one of them does not happen at the endpoints, right? The remaining case is that one of either the mean or the max does not happen, does not occur at the endpoints, right? So if it doesn't occur at the endpoints, then that means it happens in between, right? It happens in the middle of the interval. And if that is so, then we can go back to our first theorem that we proved today, right? What was our first result that we started the class today? We showed the following result, the interior extremum theorem, right? Let me put it back here. This one over here. What is it that this one said? It said that it has a maximum or a minimum in between, right? In the open interval, then the derivative is 0. Well, that's it. That's all we need, right? Then by the interior extremum theorem, we conclude that f prime of C will be equal to 0 for that value in the interior, not an endpoint, that achieves the mean or the max. And that's it. That's what we wanted, right? To show a point that has 0 derivative. Is that clear? How easy it is? So the argument is very, very straightforward. Let's go over it again. See, you know there must be a minimum or a maximum. That's the extreme value theorem, right? And then two things can happen, that the minimums and the maximums happen inside or at the endpoints. If one of them happens inside, we're done, because then we can use the theorem we did at the beginning of the class, the interior extremum theorem, and that theorem says that the derivative at that point will be 0. So that's easy. And the other one is easy too, because if both the minimum and the maximum happen at the endpoints, because the endpoints have the same height, then that means the function is constant. And if the function is constant, then it's a horizontal line, and then that means every point has 0 derivative. So that case is also easy. Yes? So one way is easy, the other way is easy. And like I was telling you, this is deceptive because we're actually using a lot of theorems, right? We're using the extreme value theorem, we're using the interior extremum theorem, and both of those require some work. But that's it. So we just show, let me put it back on the screen, the main one, Rolle's theorem, right? If we have something which is continuous in the closed interval, differentiable in the open one with the same height, then we have a 0 derivative. All right, so now we're ready to prove the main one, the mean value theorem, the one that is not the particular case, but the one that is in all its generality. I'll put it right here. So let's write the statement. So this is 5.3.2. This is the mean value theorem. And this is what it says. If f is continuous, on the closed interval AB and differentiable on the open interval AB, then there is C in the open interval AB such that f prime of C equals f of B minus f of A over B minus A. And this is the one that corresponds to the drawing I was saying at the beginning, right? So I want to, let's see if we can put both of them, yes, right here, so that we can compare them, right? How are these two similar? Well, imagine that we know 5.3.2. Imagine that we already know the proof of 5.3.2. See, and we know this extra assumption. So the Rolle's theorem has an extra assumption. The extra assumption is f of A equals f of B, right? So imagine that we have this extra assumption and we put it here. If f of A equals f of B, then this would be 0, right? And that's precisely the conclusion here. So Rolle's theorem is a particular case of the mean value theorem. And what is surprising, or maybe not that so, is that this actually is, we can prove the mean value theorem using Rolle's theorem. So in a certain sense, they are equivalent. So here's the proof, and it will be very, very straightforward. Proof. All we need to do is all we need to do is construct an auxiliary function here. So a function that it's a little bit like related to f, but it helps us out to prove this, and it's actually quite easy. So here's what we need to do. We need to construct this new function. So let g of x. See, I'm going to construct this new function, and I'm going to tell you where it comes from. So is this one is f of b minus f of a over b minus a times x minus a plus f of a minus f of x. All right, now, wow, where does that come from? Well, it's actually not that big of a deal. See, this is the equation of a line, right? You see this? This is just a line. What line is it? Well, it's a line with the slope. This is the slope of a line, and it goes through the point A, f of A. So if we go back to the original drawing, this is a line. This is a line with slope f of b minus f of a over b minus a that goes through the point a f of a and b f of b. That's what it is. So if we go back to the book, let me do that. Let's go back to the book, and we show the drawing that we started with, this one over here. So the line that I consider here is this dotted line. Let me draw on top of it. So is this one over here, this red line that I just drew on top. That's the equation of the line we have right there. Yes? So our auxiliary function is like the line minus the function. And if we do the line minus the function, it's like uncrooking it, right? Right now it's crooked. It has a slant. But if I do the line minus the function, then suddenly everything will be horizontal. And that's what I want to do, because I want to now use Rolle's theorem. Okay, so that's the trick. The entire trick is to consider that red line divided by the minus the function. The red line minus the function. Okay, let's go back to the page. And let's figure out what properties this function g has. First of all, is it continuous? Well, let's analyze it. See, this is a line. Lines are continuous. And a line, continuous function minus a continuous function is continuous. So first, that's fine. Is it differentiable? Well, yes, this is a line. A line has an easy derivative, right? In fact, if you take the derivative of this, it's just this number. And this one is differentiable too, so the difference of two differentiable functions is also differentiable. So everything works nicely here. So note that g is continuous on AB and differentiable on AB because it is the difference of a line and a function f, which is continuous and differentiable in the corresponding intervals. So I just wrote what I said so that it's very, very clear that I'm not cheating in any way, right? So this function g is continuous and it's differentiable. So good. Now, what is the derivative of this? What is g of a? Let's start with that. So what is g of a? What happens when I plug a? Well, let's see. When I plug a, over here, I'm going to get a minus a. So that's 0, right? It will be 0 plus f of a. That's the part inside the brackets, minus f of a. So that's 0, right? Okay, what about g of b? Oof, let's see, right there, g of b. What happens when we plug b? When we plug b, this will be b minus a. So it's going to be f of b minus f of a over b minus a times b minus a plus f of a. All of these minus f of b, right? I know you can barely see it, but I wanted it to look at the top and at the bottom here so that you know what I'm doing. And now the thing is that this b minus a cancels. So we get f of b minus f of a plus f of a. So the f of a is canceled. So this is just f of b minus f of b. So this is also 0, right? Okay. So we're almost done. So now this function g satisfies the hypothesis of Rolle's theorem. It's a function that is continuous in the closed interval, differentiable in the open interval, and g of a equals g of b. Both of them are 0. So therefore, we can apply Rolle's theorem. So by Rolle's theorem, there is C between A and B strictly such that G prime of C is 0. And what is the meaning of that? Let's write it. What is G prime of C? Well, what's the derivative? Let me go back a little bit. So we need to do the derivative of this part. And we already said this is a constant, so the derivative of this is 0. That's a constant, and the derivative of x minus a is 1. So the derivative of G prime at C is f of b minus f of a over b minus a. That's that constant of the line, minus, go back, minus the derivative of f, right? and we're gonna plug C. So this is true, but now I only need to solve for f prime of C. And it tells me that f prime of C is f of B minus f of A over B minus A, just like we wanted. All right, and that is it. Beautiful. So I'm gonna stop real soon now, and we're right a little bit over time, and we'll continue looking at some conclusions, some corollaries of this mean value theorem. Okay, and I also wanted to tell you in last semester I went over 5.4 because I thought I still think it's actually very, very interesting. The problem is that it was a bit technical. So my plan for this year is I want to show you at least some of the, I'm going to show it to you, but not with all the detail that is involved. And there are no exercises on that section. So it will be mostly for your general mathematical knowledge. It's in my point of view, very, very important. If you're wondering, it is about that graph that on our Canvas page, the graph that shows right there as the icon for our class. It's the graph of a function that is continuous but not differentiable, right? It is continuous everywhere and it's not differentiable everywhere. So the derivative doesn't exist at any point. At no point does the derivative exist, even though it's continuous. And that's sort of difficult to understand, right? It's hard to see. So we'll talk a little bit about that from section 5.4 next time. I'll show you some animations on Mathematica that are nice. And maybe for those that are interested, I outline or I'll write it down for those of you that want to read all the little details. But it will not be part of the course that we will test on, okay? All right. Any questions before we sign out?
Mine is just related to office hours, if anybody else has another question.
All right. So we'll talk about it next time. Thank you, guys.
Thank you.
Take care.